Welcome to another very important topic in Richard James Mathematics Resources. This is topic number 30 and is entitled Linear Programming. According to the introduction in the accompanying booklet, linear programming is one tool to solve mankind's greatest problem. In this presentation, students will be introduced to the linear programming problem and its components. The name, meaning, and use of each component will be discussed. They will also be integrated into the solution of problems. Like most other topics in functions and graphs, the understanding of this topic is dependent on the knowledge and understanding of other topics. Prerequisites for this topic may be found in the following topics that were presented in Volume 2, and Volume 2 is Functions Part 1. They include equation of a straight line and straight line graphs. Basic algebraic skills are always a requirement for all branches of mathematics. For more advanced work in this topic, matrices will play a very important role. Do not believe that you can somehow sidestep this topic. Many postgraduate degrees make use of the finer details of this topic in using computerized mathematical models in solving problems. The solution to the problem makes use of what is called an objective function. It is required to be maximized or minimized, and the category in which maximization and minimization fall is called optimization. So optimization is the single word that may be used for both maximization and minimization. There are conditions under which this maximization or minimization must take place. These conditions are expressed in a set of constraints or in a set of linear constraints. This means that the constraints are defined algebraically and can be represented on a graph where they will appear as straight lines. The statement may be summarized by saying that the linear programming problem makes use of an objective function that is optimized subject to linear constraints. So we are just going to do a little presentation of a linear programming problem, a general presentation in order that we may be able to understand the components of the linear programming problem as we solve the problems in a short while. So we are considering f of x and y, a function of x and y, 5x plus 2y. Now this is an objective function. And of course, we have a set of linear constraints. So we have our objective function right here, and we have a set of linear constraints. And we are, of course, going to maximize in this particular case, this objective function subject to the conditions that are laid out by these linear constraints. Most linear programming problems make use of tangibles. Therefore, when the constraints are being graphed, no negative values of x and y are required. Sometimes the problem lists trivial constraints as x is greater than 0 and y is greater than 0. Students are required to write constraints, but they should not include the trivial constraints. The trivial constraints are made mention of in order to remind candidates or to emphasize that the problem should not make use of any negative values. The tangibles that the linear programming problem may make use of are square feet of office space, number of items sold, number of individuals in a line at any given time, or number of employees, these are not usually associated with negative values. So here we have our original problem, the one that we are going to make a general example of. Our objective function, and we are going to maximize this objective function subject to the set of linear constraints. When the constraints are graphed, they are used in order to determine the required optimal value of the objective function. In order for a solution of the problem to exist, the straight line graphs must together form what is called a closed convex set. For work at this level, let us not worry about the convex. Just be aware that the lines must form a polygon. A sketch of the graph of the linear functions and how they are related to each other is shown below. So we have our first line. Of course, this is no means going to be a set of lines on a grid, but these lines are drawn in such a way that their relationship to each other is going to be similar to if the grid existed and they were placed on that grid. So we have another one. 2x plus 3y is less than or equal to 150. That is the line that represents that inequality. And the line that represents the other inequality, y is greater than or equal to 30, is right there. In this particular case, the region enclosed by the linear constraints is a polygon in the shape of a triangle. This is not a surprise because we have 3 of them. So we have 3 linear constraints right here. Therefore, we should not be surprised that the closed convex set in this case is a triangle. If an optimal solution exists, it does so at one of the vertices of the closed convex set. During the solution of this problem, we therefore need to take note of the coordinates of the vertices. So, if an optimal solution exists, it will exist here, here, or here. And the points that I've made mention of are the vertices of the convex set or polygon. The coordinates of the vertices of the closed convex set are given below. So now we are going to insert the coordinates. The first one, 18.75 for the x value, and the y value is 37.5. This one, x value is 30, y value is 30. And in this case, the x value is 15 and the y value is 30. And of course, if we place this polygon on a graph paper using correct scales, the value for the vertices that we have here are the same values that we would receive if we should put this on a grid. So let us examine the vertices. Remember that if an optimal solution exists, it will exist here, here, or there. Those are the points that represent the vertices of the closed convex set. Whether or not the problem is one of maximization or minimization, only 2 vertices will be in contention for the optimal spot. If this is a maximization problem, then the vertex 1530 is automatically out. There is no way it can possibly produce the maximum value of the objective function, with both ordinates less than those of the vertex 18.75, 37.5. Now, if we have an objective function that is to be optimized, there is no way that this point can give a maximum value. Reason being, right here we have in this point the x value being greater than the x value here, and the y value here being greater than the y value down here. Therefore, there's no way that this point can give the optimal solution if we are thinking about maximization. Notice that the x-ordinate of the vertex 1530 is less than the x-ordinate of the vertex 18.75, 37.5. So the x-ordinate is less, that we have it right there. Compare them, the x-ordinate is less, and of course the y-ordinate in this point is also less. So let us also compare 1530 with the other point and show that it would have been eliminated also. Now, the fact that this point causes this point to be eliminated does not necessarily mean that this point will also cause it to be eliminated. But in this particular case, the other point, 3030, also eliminates this one. Notice that the x-ordinate of the vertex 1530 is less than the x-ordinate of the vertex right here. So we have this is less than this. However, notice that for the 2 points, the y-ordinates are the same. What does that mean? That means that in this point, the x-ordinate is going to contribute less than this to the objective function. These two will contribute the same. Therefore, overall, this one will contribute less than this one. The y-ordinates being the same means that they will contribute the same amount to the objective function. However, because the x-ordinate 15 is less than 30, the overall contribution of the point 1530 will be less than that of 3030. It is automatically out of the race, and the toss-up will be between the other 2 points. So that one is out. Be aware that we do not need to compare a vertex with more than one other in order to eliminate it from the set. If we have a maximization problem, and it can definitely be shown that it will yield a smaller amount than any other vertex, it is automatically out. The next great question is, can we automatically eliminate one of the other vertices, or how may we eliminate one? Notice that the x-ordinate of the first point is less than the x-ordinate of the second. In the first point, 18.75 is less than that of the second, 30. However, the situation is different in the case of the y-ordinates. That of the first is greater than that of the second. So, in the x's, this one is less than this, and in the y's, this one is less than this. So we have the situation kind of crisscross. So what do? We therefore cannot arrive at any speedy conclusion, and the answer lies in the coefficients of x and y in the objective function. Let us examine the vertices against the coefficients of the objective function. First, classify the values of the coefficients of the objective function as large and small. The classification should not be very surprising, as 5 is larger than 2. So we are going to classify the ordinates of the first vertex in a similar way, with the larger ordinate being called large and the smaller, which is the one that goes first, is called small. So this one is the larger one. Notice that the small coefficient in the objective function is matched with the large ordinate in the vertex. So we have small coefficient with large ordinate, and notice also that the large coefficient in the objective function is matched with the small ordinate in the vertex, and again we have large matched with small. Generally, without exception, in the case that we have small multiplied by large or vice versa, in a maximization problem, the objective function eliminates the vertex that is involved. So this one is going to be eliminated. Why? Because we have small going with large and a large with small. So this one is going to be eliminated. Because one of the remaining vertex was eliminated by the objective function, the only one that is left will result in the optimal solution. So the ordinates of the other vertex are equal and will therefore not be classified as small or large. It is, however, worthy of note that the number 30 in this case, that is multiplying the large coefficient of the objective function, is larger than the one, which is 18.75, used when examining the previous vertex. So these cannot be classified as large or small because they are both the same. But if we could take a look in hindsight, we'll realize that the value that we have here to multiply this large value of the objective function, because in the objective function the 5 is the large value, notice that this one is larger than the one that is used to multiply in the other vertex. So this vertex will contribute a greater value to the objective function and will be our optimal vertex. Generally, without exception, the vertex that has the largest ordinate multiplying the large coefficient in the objective function will yield the maximum result. That is desirable in a maximization problem. Let us verify that the point 30, 30 will actually give the maximum result. Substituting the x and y values of the vertex in their respective places in the objective function will yield the following result. So we have the x value accompanying the x coefficient, and of course the y value accompanying the y coefficient. 5 times 30, 150, and 2 times 30, 60. And when we add those, we have 210. So let us do the same with the vertex 18.75 and 37.5 for the y ordinate, and let's see what happens. The value turns out to be 168.75, which is actually smaller than the one that we have here. So of course we are sure that the point 3030 will yield the optimal solution. The point 3030 gave the largest value of the objective function, confirming the result of our analysis. As we move on to our problem solving section, we will not continue to perform the analysis in detail, but just make use of the principles that we have already proven to be valid. So we have our first problem to solve. The table shows the cost of tuition per week for a private school. The conditions under which a school operates are as follows. The maximum number of places at the school is 75. There must be a minimum of 20 full-time pupils. The number of part-time pupils must be at least half the number of full-time pupils, the minimum weekly income must be $6,000. Let X represent the number of full-time pupils and Y represent the number of part-time pupils. Write 4 inequalities not including X is greater than or equal to 0 and Y is greater than or equal to 0 to represent the conditions stated above. Of course, we know that these are the trivial inequalities because in the linear programming problem in general, we make use of tangibles that don't generally have negative values. Use a scale of 1 centimeter to 5 units on both axes. Draw the graphs of the inequalities. If the profit on each full-time pupil is $40 and that on each part-time is $30, determine from your graph the number of full-time and part-time pupils for the maximum profit to be obtained, the sum representing the maximum profit. And of course, as we flip the page, all of the statements of the problem are gone. So it is strongly recommended that if you need to follow this with information popping up all the time, that the accompanying booklet, the booklet that accompanies this video, may be used as your accompanying document that will keep you up to date with the information in the problem. But of course, as we attempt to solve each part of the problem, the statement pertaining to that part of the problem will be highlighted. So we have read through the problem. This is more than a mouthful. Now, of the great amount of information, what is the first thing or set of things to consider? And in any linear programming problem, this is what we do. Let X represent the number of full-time pupils and Y represent the number of part-time pupils. Write 4 inequalities not including X is greater than or equal to 0 and Y greater than or equal to 0 to represent the condition stated above. So, let X represent the number of full-time pupils. Let Y represent the number of part-time pupils. In a linear programming problem, we need to determine what the variables represent first. So that is our first task in solving a linear programming problem. It says now the maximum number of places at the school is equal to 75. So of course we are going to write 4 inequalities, and the first statement that we will write our inequality on is this one. The maximum in any situation is the largest value. Therefore, no value can be greater than the maximum. It must be either less than or equal to. And of course, the total amount or the total number of students is represented by the number of part-time plus the number of full-time. So X plus Y is the total. Put in your part-time and your full-time together, and that should be not greater than 75, should therefore be less than or equal to 75. There must be a minimum of 20 full-time students. The number of full-time pupils is represented by X. The smallest value of X is 20. According to what we have here, the minimum is 20. So if the minimum is 20, we cannot go lower than the minimum. So it should be either greater than the minimum or equal to the minimum. So X is greater than or equal to 20. No figure can be less than the minimum. It must either be greater than or equal to. Of course, we are reminded there that X represents the number of full-time pupils and Y represents the number of part-time pupils. The number of part-time pupils must be at least half of the number of full-time pupils. So the number of part-time pupils must be at least half of the number of full-time pupils. We already know that at least means greater than or equal to. The statement means that the number of part-time, which is y, must be greater than or equal to half of the number of full-time. So y is greater than or equal to a half of x. The minimum weekly income must be $6,000. Again, the minimum means greater than or equal to. Nothing can be less than the minimum. It has to be greater than or equal to. Most students would have forgotten the information given at the beginning and write this down. X plus y is greater than or equal to 6,000. But this has a serious flaw. X and y represent the number of pupils, and the 6,000 is in dollars. There is no way we can add number of pupils and get our answer in dollars. That is just going to be impossible. Remember the type and of course the fees charged on each one. We have them right here. The income contributed to the full-time pupils will be equal to the product of the fees per full-time pupil and the number of them. So the fees that will be contributed by the full-time pupils, you take the fee for each pupil and you multiply that by the number of full-time pupil. And of course, the number of full-time pupils will be X. And of course, we're going to do the same thing with the number of part-time pupils. And the number of part-time pupils is equal to Y. So we are going to take Y and multiply by the fee for each part-time, which is 100. And we are going to take the X, which is the number of full-time, and we are going to multiply that by the amount for each full-time pupil. So the inequality should rightly be written 200x plus 100y is greater than or equal to 6,000. Of course, we have our money right here and more money here. So we are sure that if the answer that we have is $6,000, that in terms of the units, we are correct. Now, it is time for us to graph the inequalities. We may recall or revisit the principles covered in equation of a straight line and straight line graphs. Be aware that the grid presented here is not of the same dimensions as those on your typical graph paper. The scales may not look the same, but the diagrams will be proportional to each other. So if you put this on a grid, on a graph paper, it is going to be in the same proportion as the one that we have here, but they will not be the same size. So inequality 1, x plus y is less than or equal to 75. Remember that when graphing straight lines of this nature with x and y on the left hand side and a constant on the right hand side, we equate one of the unknowns to 0. So then if we have x plus y is less than or equal to 75, and of course that is going to be related to the line x plus y is equal to 75. And if that is the line that we are graphing, x plus y is equal to 75, if x is equal to 0 and the sum of them is 75, then y must be equal to 75. One point as coordinates, the x part is 0 and the y part is 75. So we're going to plot that point. X is 0 and y is 75. The point will go right there. We can do the same with the others. The coordinates of the other may be shown to be 75, 0. And how do we get that? We will get that by saying if y is equal to 0, then x is equal to 75. We may plot the point. So we're going to plot that point with x value is 75 and y value is 0, no upward movement, so the point is right there. We may draw the straight line through the points. Remember that we need only 2 points in order to graph a straight line. So this is our line that is related to this inequality, and this line has equation x plus y is equal to 75. If candidates are encountering any problems with the graphing of the lines in detail, remember that we have 2 topics: equation of a straight line and straight line graphs, in which the graphing of straight lines is discussed in detail. So we have another one, inequality 2. X is greater than or equal to 20. This new inequality is related to the line x is equal to 20. From our study of equation of a straight line, we know that this represents a line that is parallel to the y-axis and crosses the x-axis at 20. So the line is going to be right here. That is our line. X is equal to 20. Inequality 3. Y is greater than or equal to a half of x. We have graphed similar lines before. The only hint is that y is always half of x. According to what we have in the inequality, if we are going to graph the related straight line, we are going to graph y is equal to a half of x. Now, the only hint is that y is always a half of x. This will suffice, but we will have to pull the values of x out of a hat. So we will have to arrive at our values of x all on our own. And that is not very difficult. So choose the values of x. And the reason why we are choosing even value is that we try to avoid using any fractional values unless we have to. So if we say x is equal to 80, then y is going to be equal to a half of 80, and we are going to plot that point. So 80, 40. If x is equal to 80, half of 80 is 40. The value of y is 40, and the coordinates will be 80, 40. And we may plot that point. So 80, 40, let us plot that point right there. Of course, we may choose another convenient value of x. Say x is equal to 60. Half of 60 is 30. The point will be the x value is 60 and the y value is half of that, which is 30. So we're going to plot that point 60, 30. If x is equal to 0, a half of 0 is 0. The line will therefore pass through the origin, whose coordinates will be 0, 0. The line will therefore pass through those points, and let us draw that line. Good. Inequality 4. 20x plus 100y is greater than or equal to 6,000. The associated line is of a familiar nature. Of course, the x and y are on the left hand side and the constant is on the right. And in this case, we usually equate x to 0, find the equivalent value of y. So this one is of the type that we equate one of the variables to 0. So let x equal 0. If x is equal to 0, this one is gone. And 100y is equal to 6,000. And this is what we have right there. So 1y, or just y, is equal to 60. So the coordinates of the points are 0, 60. So let us plot that point. The x value, no movement in that direction. The y value is 60. Right there. And of course, the same inequality, and this time we are going to equate y to 0. Y is equal to 0. What happens? This part is gone. 200x is equal to 6,000. And when we divide that, we get x is equal to 30. So that point is going to be 30, 0. We're going to plot that point, by the way. 30 for the x, no movement for the y. The point is right there. Draw the line joining 0, 60 to 30, 0. And that is your line. We now need to identify the region that satisfies all of the inequalities. This is usually quite easy, as the region may be the only region that is bounded by all of the inequalities. However, to prove that we are correct, we will perform a simple analysis. First, we need to understand what greater than or less than means on the rectangular coordinate system. Notice that the value of x increases to the right. If any inequality indicates greater than a particular value of x, the region concerned is to the right of that value. So x increases in that direction. The value of y increases upwards. If an inequality indicates greater than a particular value of y, the region concerned is above that value, going up all the time for greater than a value of y. If an inequality indicates greater than a combination of x and y, then the location of the region is in a diagonal direction, indicate that it is going to the right and going above at the same time, and that is shown by that purple arrow, going to the left, going to the right, and going up at the same time. The less than regions will be opposite to those previously indicated. So then, if we are going less than a value of x, we are going to go in that direction. If we are going less than a value of y, we are going in that direction. And if we are going less than a combination of x and y, we'll be going in that direction. So, to the right is a sketch of the graph of the inequalities. The first one is x plus y is less than or equal to 75. This is it. This is a combination of x and y, and with the less than or equal to sign, the region is diagonally downward in relation to the line x plus y is equal to 75, which is this line. So we are going to go like that, less than. So we are less than both x and y values on this line. So that is the direction that we are talking about. So let us consider x is greater than or equal to 20. The region is to the right of the line indicated by x is equal to 20. So this is our line, x is equal to 20, and we need to go to the right of that line. The other one, y is greater than a half of x. This will specify the region that is above the line y is equal to a half of x. Notice that although we are going above, there's a reason why the region is not identified by a diagonal that is to the right and upwards, but one that is to the left and upwards. If we transpose the inequality, the result is y minus a half of x is greater than or equal to 0. The negative coefficient of x indicates that our movement is in the negative x direction, and this is to the left, so we go to the left and upwards. Finally, the region must also be located in the region upwards and to the right of the line 100y plus 200x is equal to 6,000 in that region. The statement of the problem did not require that we shade the region, but let us do so for clarification. So let us show where the region is involved, right there. So of course the region is going to be this region of space that we have right there. We now need to identify all of the vertices of the region specified by all of the inequalities. So vertices, and we have them right there. Also they are in the diagram, and they are also on our answer sheet right here. If we can identify any point with both ordinates less than those of any other point, then we may eliminate that point. We now have a maximization problem. So if we can find any vertex in which the two ordinates that are less than the two ordinates of any other vertex, then we know that that one is out. So look at this one now, just to clarify what we mean. If we compare 2412 with 5025, so we have 2412 with 5025. The 24 is less than the 50 and the 12 is less than the 25, so that point is automatically out. Will not be able to contribute the optimal values, so that point is out. 2020 will suffer the same fate with both ordinates less than those of 50, 25. So of course this one is automatically out also. 50, 20, 25, 20. So these two are less than these two, so that point is out. Why can't we automatically eliminate any of 20, 55 and 50, 20? Because in one point the x ordinate is larger, while in the other point the y ordinate is larger. One will have to be eliminated by the objective function. So here we cannot eliminate any of these because both of the ordinates here are not less than both here. Or we can say both here are not greater than the two that we have here. So we will have to eliminate one of them by making use of the objective function. We will not be able to proceed beyond this point without the objective function. What is the clue that will help us to derive the objective function? The profit on each full-time pupil is $40, and that on each part-time is $30. The profit can be found by multiplying the number of students by the profit on each student. The profit on each student falls into two categories, one for full-time and the other for part-time. Recalling that the number of full-time students is equal to x and the number of part-time is equal to y, the objective function is number. The x here represents the number of full-time, and that is multiplied by the profit on each full-time. And here we have the number of part-time multiplied by the profit on each part-time, and that gives the total profit. And that we have there is the product of the profit on each full-time pupil and the number of full-time pupils. And on this side we have the product of the profit on each part-time pupils, and that we multiplied by the number of part-time pupils. Let us examine both vertices against the objective function as before. The terms large and small will be used as before, and we will begin with the point 20, 25. So, of course, let us put in our large tag and small tag, and we take our first vertex and we put a small for the smaller one and a large for the larger one. Right? There we have the rectangles that are grouped in the large and the small to show you how these are going to be associated with each other. Of course, there we have it again, and of course we have the large tag and we have the small tag. We have our other vertex, and of course that's what we have on that right hand side over here. Good. The vertex that has the large ordinate multiplying the large coefficient in the objective function is 5025. This will give the optimal solution of the problem. So the one that takes the large ordinate and multiply the large coefficient, that one will give the optimal solution, and the other one is out. Notice that in the statement of the problem, we are required to find the number of each category of students that will give the maximum profit before calculating the maximum profit. This means that there must be a way to determine those values without experimenting with each vertex and the objective function, as we have done. So, instead of substituting the x and y ordinates of each vertex into the objective function, there's a way that we can tell which vertex will give the optimal solution, and it is usually the vertex that takes the largest value of the ordinate to multiply the large value in the objective function. Finally, we need to find the sum that represents the maximum profit. This will be done by substituting the values of x and y in their respective positions in the objective function. So that is our objective function, and we know that we are dealing with the point 5025. So we put the ordinates in their respective places, and the result is $2,750, and that is the maximum profit. Students may want to use a quick analysis in order to determine the vertex that will give the optimal solution. In the case of a maximization problem, the vertex that uses the largest value to multiply the large coefficient in the objective function is usually correct. In writing down the inequalities, some students have developed the bad habit of using one inequality as a clue to finding out what the other one should be. This is outrageous. The inequalities are not related to each other, and there is nothing about one that should affect the other. The inequality on the left, which is y is greater than or equal to a half of x, is heavily loaded by CXC. According to the statement of some problems, it will be disguised in the following forms. So this is a simple inequality that we have graphed already, and it has a tendency to return and to return time and time again. But sometimes it is disguised in different forms, like this one. 2y is greater than or equal to x, or x is less than or equal to 2y. Irrespective of this appearance, it should be graphed in the same way. Examiners may realize that students are expecting y is greater than or equal to a half of x to be given in a strange form, and give instead y is less than or equal to 2x, which of course is different from all of the forms of y is equal to a half of x. So they expect you to sometimes anticipate y is greater than or equal to a half of x in some other form. So they give you another inequality, and you think that it is y is greater than or equal to a half x that is disguised, but in fact sometimes it's a different inequality. So because of preconceived notion, some students will see x is less than or equal to 2y. So what do we have here? Y is less than or equal to 2x. But because students have this prior conceptualization of the problem before actually seeing the problem, students see x is less than or equal to 2y and end up drawing the wrong line. Now we have another problem. A manufacturer produces two types of ballpoint pens, type L and type M. There are at least 50 of type L and at least 25 of type M pens. The manufacturer, however, does not produce more than 80 of type L or more than 60 of type M or more than 120 of both type L and type M taken together. Using X to represent the number of type L pens produced and Y to represent the number of type M pens produced, write three inequalities, not including the trivial inequalities that we have discussed already, not including X is greater than or equal to 0 and Y is greater than or equal to 0, which represent the above conditions. Using a scale of 1 cm to represent 10 pens on each axis, draw the graph of the inequalities. The manufacturer makes a profit of $1.50 on each type L and $1.10 on each type M pen. Write an expression to represent his total profit, and of course that is going to be our objective function. Use the graph to determine the values of X and Y which give a maximum profit, and hence determine the maximum profit. And of course, notice that as a requirement, we are required to find what? X and Y values that will give the maximum profit before finding the maximum profit. So we are sure that we must have some way, without actually calculating the profits in every single case, to determine the X and Y values that will give the maximum profit. Then we may proceed to find the maximum profit. Follow in your booklet if there is any problem remembering any detail of the statement that we have just read. Always remember that a good place to begin is to write down the meaning of X and Y, the values that will occupy the axes. So X is equal to the number of type L pens and Y is equal to the number of type M pens. There are at least 50 of type L and at least 25 of type M pens. What do we mean by at least 50? 50 is the least. So the value must be not less, because it cannot be less than the least, must be greater than or equal to 50. So remember that if a particular value is the least, other values may be greater than or equal to that value. Nothing can be less than the least. So must be greater than or equal to 50. And of course, the same applies to the Y's. At least 25. Nothing can be less than the least, must be greater than or equal to 25. The manufacturer, however, does not produce more than 80 of type L or more than 60 of type M pen. Does not produce more means he may produce that amount or less. So does not produce more means less than or equal to. So if he does not produce more than if he does not produce more, then he produces the same amount or an amount that is less. So does not produce more produces the same amount or an amount that is less. So X is less than or equal to 80. And the same applies to Y. The manufacturer does not produce more than 120 of both type L and type M taken together. So what do we do when we take them together? Simply add them. So the total of X and Y cannot be more than 120. It must be less than or equal to 120. The statement of the problem requires 3 inequalities, and we have 5. We need to reduce our list to 3, and this may be done by combining similar inequalities. So there are our 5 inequalities. We may first cause the inequality sign in the x's to be the same and those in the y's to be the same. So here we have x is greater than or equal to 50 and x is less than or equal to 80. So we are going to write this one. Of course, if x is greater than or equal to 50, it means that 50 is less than or equal to x. That we have right here. And this one, if y is greater than or equal to 25, it means that 25 is less than or equal to y. So we are going to combine those two, and this combination or this representation of an inequality is by no means strange. In functions part 1, we had the region in which we are required to plot a graph given in a similar way. So these also may represent the boundaries. The boundaries in which we are required to plot the graph was given in this format, and we interpreted it at that stage to mean that the values of x will begin at the lower limit and will go to the upper limit, and because of the or equal to, that means 50 is included and 80 is included. So this is quite similar to what we have seen and used before. And of course we are going to do that with the y's. We are going to combine those two inequalities. Now we have 3 inequalities. The new inequalities may be interpreted as that x lies between 50 and 80 inclusive. Or we may say that 50 is less than or equal to x, while x is less than or equal to 80. We have our 3 inequalities, and we may proceed to graph them. Remember that the grid that we will use is not of the same dimensions as those on your graph paper. The scale may not be the same as required by the statement of the problem, but the one that will be constructed will be proportional to the one on your graph paper. The first inequality will be 50 is less than or equal to x is less than or equal to 80, and that is related to 2 lines. It is related to the lines x is equal to 50 and x is equal to 80, and those are 2 lines that are parallel to the y-axis that cross the x-axis at x is equal to 50 and x is equal to 80. There we have them. And of course that one is related to the lines y is equal to 25 and y is equal to 60, and are 2 lines that are parallel to the x-axis that cross the y-axis at y is equal to 25 and y is equal to 60. There we have them. Y is equal to 60, y is equal to 25, as we have them right here. Remember that for the inequalities like the ones that we have with the x's and y's on the left hand side and the constant on the right, we usually equate the x to 0 and the value of y will be equal to 120. And if we equate the value of y to 0, the value of x is going to be equal to 120. Considering both cases, the points will be 0, 120, and 120, 0. So 0, 120, 120, 0. So draw the line joining the ordinates of 120 on both axes. So the line is going to go from this point to that point. And that is our line. X plus y is equal to 120. There we have now all the vertices. Now we have completed the closed convex set, which is our polygon, of course, with all of the coordinates of the vertices included. So we have included all of the coordinates of the vertices as we can see them there. Put them under the microscope. We may rewrite them on our answer booklet. The objective function is p is equal to 1.5x plus 1.1 y. The large value of coefficient in the objective function belongs to x. We therefore need to find the vertex with the largest x value. The larger coefficient belongs to x. So we are going to look here to find the vertex with the largest x value. There are two of them, and they are 80-40 and 80-25. We are sure that the one that will give the optimal solution is the one with the larger y value. Of course, for the largest x value we have 80, but there's a tie between 2 points. So the x ordinate will contribute the same. Therefore, the one that will contribute the greater amount for the y ordinate will therefore be the optimal solution. So this one is the one that we are going to choose. The vertex is therefore 80-40, x is equal to 80, and y is equal to 40. Although the region that satisfies all of the inequalities may be easily identified as the one enclosed by all of them, let us take a look at how each inequality confirms our choice. So let us draw a sketch to show the relationship among the lines. Right. According to the first inequality, the region must be between the lines x is equal to 80 and x is equal to 50. And these are the two vertical lines that represent those inequalities. Right there. So the region must be between those two. According to the second inequality, the region must be between y is equal to 25 and y is equal to 60. The third inequality has the combination of x and y, and its sign is less than or equal to. This indicates a diagonal that goes down and to the left at the same time. Less than for the x and less than for the y. Let us now shade the region. So that is our region. If the profit on each type L is $1.50 and that on each part M is $1.10, then the total profit will be the product of the profit on each pen multiplied by the number of pens. Remember that the number of each type L is x and that of type M is y. The total profit may therefore be given by the objective function. So the profit on each multiplied by the number of each. Remember that x represents the number of type L. So it's the profit on each type L multiplied by the number of type L's, and the profit on each type M multiplied by the number of type M. Insert the optimal values of x and y into their respective places in the objective function, and remember them. If we don't, then we are going to be reminded right there. 80 for the number of type L and 40 for the number of type M, and of course 1.5 of 80, half of 80 is 40, so let us add 40 to 80, we get 120. And of course we have 1.1 multiplied by 40, that is going to be 44. So 120 plus 44, and that is equal to $164, and that represents our maximum profit. Now this is another problem I like because it's short and some other reasons. A boy has $280. He wants to buy X records at $35 each and Y tapes at $40 each. He must buy more than one tape but not more than 4 tapes. He must also buy at least 3 records. Write 3 inequalities in X and Y to represent the above information. Using a scale of 2 centimeters to represent 1 unit on each axis, draw the graph of the inequalities. Shade the region that satisfies the 3 inequalities. Determine the maximum amount spent and state the XY value that gives this amount. This is my all-time favorite linear programming problem for reasons that we will soon discover from the beginning to the end. As usual, begin by identifying the meanings of X and Y. So X is the number of records and Y is the number of tapes. He must buy more than 1 tape but not more than 4 tapes. He cannot buy 1 tape. It says what? Must buy more than 1. So he cannot buy 1. So he cannot buy 1 tape. The number of tapes must be definitely greater than 1. Not more than 4 means that he may buy 4 or less. So Y is greater than 1, should be greater than 1, cannot be equal to 1, and Y is less than or equal to 4. He must also buy at least 3 records. We cannot get below the least, the number must be greater than or equal to. There we have 3 inequalities, but they cannot be the 3 expected by the statement of the problem. As we will show, while graphing them, they do not form a closed convex set. And this is my first reason for enjoying this problem. My second reason is that the third inequality is given implicitly instead of explicitly. Since he has a fixed amount of money, which is $280, there is an upper limit of $280 that he can spend. Therefore, with the cost of each record being $35 and that of each tape being $40, multiplying those prices by their respective numbers must yield a sum that is less than or equal to $280. The inequality is therefore 35x plus 40y is less than or equal to 280. Rearranging the inequalities in y as before results in the list of inequalities that we have down here now. Remember that these two will have to be combined to form one inequality. And of course, as you will see, let us combine the y inequalities as before, and this one is smoother than the two that we had before. So when we combine them, this movement is smoother than the one that we had before. Right. So now we have our 3 inequalities, and we may proceed to graph them. So we have our first one. 1 is less than y is less than 4. The graph of the first inequality will be represented by 2 lines parallel to the x-axis, crossing the y-axis at y is equal to 1 and y is equal to 4. Because the value of y cannot be equal to 1, the line at y is equal to 1 is represented by a broken line. And the other one, of course, will be an unbroken line. So y cannot be equal to 1. So at y is equal to 1, we have a broken line. And then here we have an unbroken line. The other one is x is greater than or equal to 3, and of course that's what? An unbroken line parallel to the y-axis and touches the x-axis at the point where x is equal to 3. So that's your point. And of course we have another one. Notice that graphing the first two inequalities did not result in a closed convex set. So remember, here we have 1, 2, and we have another one. So if these were the three inequalities that we should use, we would have a serious problem because we need to have a closed convex set. And these three inequalities would not have given that closed convex set. So we need to include the other one. And of course, it is in our familiar format with the x and y on the left hand side and the constant value on the right hand side. And we usually equate one of them, in this case x is equal to 0. So when x is equal to 0, this part is gone and we have 40y is equal to 280. So y is equal to 280 divided by 40, and that will give y is equal to 7. And we are going to do the same with the other ordinate in a short while. So the point is 0, 7, and the line will cross the y-axis at y is equal to 7. Next, let y is equal to 0. What happens? 35x is equal to 280, and when we divide 280 by 35, we get 8. The ordinates of the other point will be 8, 0. The line will therefore cross the x-axis at x is equal to 8, and the y-axis at y is equal to 7. That's our line. Let us write down the coordinates of the vertices of the closed convex set. So those are the coordinates of the vertices on the graph paper and also in our answer booklet. The objective function is implicit and is hidden in one of the inequalities. This is my third reason for enjoying this problem. Let us write it down and give the reasons later. So we have p is equal to 35x plus 40y. My fourth reason is that although it has no bearing on the result, the larger coefficient belongs to y, which is in its less frequent position. Usually the larger coefficient in the objective function usually belongs to x. In this case it belongs to y. This has unsighted candidates in examinations, so students sometimes don't realize, although it is blatant in front of their faces, that the y ordinate is the larger one, although it has no bearing on this problem to the extent that it will affect the choice of vertex. It will not affect the choice of vertex. So here we have them. We are attempting to maximize the amount of money spent. This amount may be expressed algebraically as the sum of the product of the cost of each item and the number of each item. It is therefore expressed as follows. So this is the number of items and this is the number of items, and we are multiplying the number of items by the cost of item, the number of items by the cost of item, and that is our objective function. The P does not mean profit. We may use any letter to represent the amount spent. Traditionally, linear programming problems make use of profit, so we are using the P in this case also. Before demonstrating that we are experts on solving linear programming problems, let us be reminded of the fact that the value of y cannot be equal to 1. So before we jump jumping to conclusion is bad exercise. So before we jump, we need to be reminded that 1 cannot be a value of y according to the inequality that we have, right? Those points in which the y ordinate is equal to 1 are therefore automatically and mathematically out. Remember, y has to be greater than 1 according to one of the inequalities. Not greater than or equal to, but greater than 1. So those that have 1 are automatically out. 1 in the space of y, those are automatically out. My final reason for enjoying this problem is that with y ordinates of the remaining points being equal, a choice of the point 3.5, 4, in which the x ordinate is larger, should be the optimal vertex. This is impossible as the boy cannot buy a fraction of a record. The only vertex that is worthy of consideration is therefore 3, 4. No fraction of a record or tape. Therefore, 3, 4 is our only consideration. So P is 35x plus 40y. That is our objective function, in that we introduce our values 3 and 4 in their respective places, and our solution is P is $265, and that is the amount, the maximum amount that will be spent. The problem also requires that we shade a region that satisfies the inequalities. We will proceed to show how we may be able to positively identify that region. Let us draw a sketch to show the relationship among the lines. According to the first inequality, the region must be between the lines y is equal to 1 and y is equal to 4. According to the second inequality, the region must be to the right of x is equal to 3. The third inequality has the combination of x and y, and its sign is less than or equal to. This indicates a diagonal that goes down and to the left at the same time. So let us now shade the region. Of course, we realize that the region is in this particular area. So that's our region, nicely shaded, or shaded but not nicely. We are shading it here because if we put that on the grid, although in the examination students are required to shade it on the grid, if we shade it on the grid on this computer, it will make a meal of the entire diagram that we have. Now we have our final problem. A florist uses X lilies and Y roses to make bouquets. The total number of flowers in a bouquet must be less than or equal to 45. Write an inequality in X and Y to represent this. Write an inequality in X and Y to represent this condition. There must be at least 10 lilies in the bouquet. The number of lilies is less than or equal to twice the number of roses. Use a scale of 1 cm to 5 units on each axis. Graph the inequalities in 1, 2, and 3. The profit on a lily is $1 and the profit on a rose is $2. Write an expression for the total profit made on a bouquet. Use the graph to determine the maximum profit that could be made on a bouquet. Let us begin by identifying the meanings of X and Y. X is the number of lilies and Y the number of roses. The first statement to be used in writing the inequality is as plain as one can get. it uses the term less than or equal to, so we have no doubt that it should be less than or equal to. But of course, we need to have the total number of flowers. X plus y is less than or equal to 45. There must be at least 10 lilies, and by now we are sure what this means, greater than or equal to 10, because we cannot have anything that is less than the least, must be greater than or equal to. The number of lilies is less than or equal to twice the number of roses. Here's our good friend. X is less than or equal to 2y. The only problem that we may encounter is caused by the way that the third inequality is stated. It is written in one of the forms that we might expect for y is greater than or equal to a half of x, which is the one that we have graphed before, which is the one that we warn that CXC likes to give in another form. However, we may transpose the inequality making y the subject. So if we transpose that, what do we have? We put the y on the left hand side. So where we have x is less than or equal to 2y, now we have 2y is greater than or equal to x. And of course, 2y, so because 2 is being multiplied by y here, we divide by 2 on the other side. So y is greater than or equal to a half of x, or we may say x over 2. And that is our lovely inequality that we expect, and that we were not disappointed. Whenever an inequality or equation has only two terms, one in x and the other in y, in order to prepare it for graphing, it is best to transpose it, making y the subject. X plus y is less than or equal to 45, and that is one of our good friends. By now we should be able to look at the inequality and graph it. When x is equal to 0, y is 45, because we have this format where the x and y values are on the left and the constant value is on the right. So when x is equal to 0, y is 45, and when y is equal to 0, x is 45. The line will therefore pass through 0, 45 and 45, 0. This will cross both axes at 45. So we may just put that in right there. And of course, x is greater than or equal to 10 should pose no alarm. Line that is parallel to the y-axis and crosses the x-axis at x is equal to 10. There we have it. And of course, that line is the line that is related to this inequality. Y is equal to a half of x. We have graphed that before, so we just drop it in right there. Or we can start to say that if x is 40, y is half of 40 is 20. Is going to pass through x 40 and y 20. If x is equal to 30, is going to pass through 30, and half of 30 is 15, is going to pass through that point. And of course, is going to pass through the origin. So we have graphed this line before. Y will always be a half of x. So the line will pass through 40, and a half of 40 is 20, so it will pass through 40, 20. X is 40, y is half, so y is 20. And here we have, for 30, 15, y is a half of x, so x is 30, y is 15. And also it will pass through 0, 0. A half of 0 is 0. So it will pass through the origin. And there we have it. Let us identify the coordinates of the closed convex set. Right, so we have them. One here, 10, 35. One here, 30, 15. And another there, 10, 5. Now, with the x-ordinate of the point 10, 5 being less than that of 30, 15, and the y-ordinate of 10, 5 being less than that of 30, 15, the point 10, 5 does not stand a chance in the maximization. So of course, which one does not stand a chance? This one. Because in this case, 10 is less than 30 and 5 is less than 15. So both ordinates are less than both ordinates here. And of course, if we compare it with this, it is still out because the x ordinates are equal and the y ordinate here is less. So this will definitely contribute less to the objective function than this. So both other points will eliminate automatically 10, 5. So that's out. The profit on a lily is $1 and the profit on a rose is $2. The objective function is therefore p is equal to x plus 2y, or we might say p is equal to 1x plus 2y. But of course, a coefficient of 1 is not necessary, so we may say p is equal to x plus 2y. The coefficient of y in the objective function is larger than that of x. Of course, 2 is greater than 1. We will seek after the point that has the largest y ordinate. Because the coefficient of y is a large one, this time we will search for the point that has the largest y ordinate. That one is out. We may conclude by substituting the value of x and y in their respective places in the objective function. Of course, we have e is equal to 10 plus 70, and that we have the maximum profit is $80. Let us identify the region that satisfies the three inequalities. Do not forget that in most cases it is a region that is bounded by all of the lines in the graph. So let us draw a sketch to show the relationship among the lines. There we have that. According to the first inequality, the region must be diagonally below the line x plus y is equal to 45, which is this one. In that direction. And according to the second inequality, the region must be to the right of x is equal to 10. And this is our line, x is equal to 10. And the third inequality discussed in the first problem, and we know that we have the arrow pointing in that direction, and we have the reasons there also in our first problem. So let us shade the region. In order to emphasize the importance of mathematics in general and linear programming in particular, I will relate a story about one of my past students. I presented mathematics at the CSEC level to one of my students. She hoped that it would be the last time that she would have anything to do with the subject. It so happened that when she was reading for her associate degree, I lectured to her again. She was sure that this associate degree encounter with mathematics would be her last. She then enrolled in a postgraduate program. In the introduction to the program, she encountered some serious mathematics courses, one of which required that she use mathematical models on a computer system to solve linear programming problems. If her foundation in mathematics was not strong, she would not have advanced further than the first set of courses. I have had to tutor many other students that were attempting postgraduate courses related to linear programming. The students attended different institutions, home and abroad, but the requirements were similar. We may therefore conclude that this topic is a very important introduction to many of your future courses of study.